All right, so having done this for 0.1 and now you've done it for 0.01 and 0.001, you've found the delta for each of those. You should have a nice little chart that sort of looks like this. I'm gonna make it look a little more charty. There, is that charty enough for you? Hope so. And the next thing that I'm asking you to do with it is verify that delta is equal to the square root of epsilon cubed. All right, so what we're always looking for with epsilon and delta is a relationship between them. The delta is in fact determined by epsilon. One of my professors emphasized delta is a function of epsilon. One of the reasons that we know that delta is always equal to the square root of epsilon cubed is just the process by which we got it. How do I solve this equation every time? I cube both sides, and then I take the square root both sides. I'm going to do that every time. Then I'm going to be keeping in mind that I'm really looking at an interval, so when I take that square root, I'm really looking at the positive and negative square roots, but they're sort of bracketed out by this absolute value, which is crucial. All right, so that's one way to verify that. You can also just go in your calculator and do, 0.01 cubed and take the square root of it. Yeah, you're going to get 0.001, and you can do the square root of 0.001 cubed, and you're going to get my calculator put it in scientific notation 3.16 times 10 to the negative fifth, but since you guys did excellent in 8th grade, you know that that's equal to 0.0000316. Okay, now the next thing I want to show you about this relationship is, where is all this stuff on the graph? All right, where is epsilon, where is delta? So when we say, as we did in the previous page, that if absolute value of x is less than 0.0316, then the absolute value of f of x minus 0, so I guess I'll put it anyway, is less than 0.0316. So that's for the it's less than 0.1. So that's the statement using our first epsilon. Okay, where are this epsilon and this delta on the graph? So it's like this. Epsilon is a constraint on how close I want the y values to be to the limit. So the epsilon is on the y-axis. So in particular, that epsilon of 0.1 is here. Well, I'm going to put it up here, just to give myself a little more space. This is 0.1, all right? But we're saying absolute value of f of x minus L is less than 0.1. That means although for this function, f of x does not happen to be less than L, for some other function it could be. So this absolute value of f of x minus L is less than 0.1, means if I go 0.1 above the graph and 0.1 below the graph, so negative 0.1, below the limit actually, what I'm really looking at is what's called an epsilon band. All right, so this is a wide road, okay, this street. This is epsilon up here, and this is negative epsilon. All right, this is epsilon equals 0.1. This is, negative epsilon equals negative 0.1. I guess you could say it like that. All right, so what this is saying is, where's the delta? We're saying that if the absolute value of x, so that's on the x-axis now, is less than 0.0316. So what that means is if I take my delta, I'm going to be looking at the values that trap the function within the epsilon band. So this is called the delta band this way. So here's delta equals negative 0.0316, so my axes are scaled unequally, which is okay. We do that sometimes. Delta equals positive 0.316, and this is the delta band. So what this statement is saying is, if I constrain the x's to be within a delta band that has a width of 0.0316, that's what this is saying, then the f of x's, the red points, will be constrained to be within 0.1 of the limit. So where are the limit and the c? So this is L, in this case happens to be 0. We will see cases where it's not 0. And this is c. C is the x-axis in this case because c is also 0. So sometimes we'll see that the L is not 0, the c is not 0. All right, so that's a delta band that goes with epsilon equals 0.1. So what happened when we go to epsilon equals 0.01? So I'm going to cheat a little bit with the scaling and say that 0.01 is here. Of course, it actually would be tighter in. So here's an epsilon band of 0.01. So here's epsilon equals 0.01, epsilon equals negative 0.01. So now what I'm doing is saying if I took a smaller epsilon band Could I still get all the red points to land in that epsilon band? So the answer is yes. All I have to do is take a smaller delta band. So I take the delta to be here to here. So now I've taken a smaller delta band. This is delta equals negative point. This is negative delta over here. 0.001, and this is delta equals positive 0.001. So the idea is big epsilon band, big delta, smaller epsilon band, smaller delta, even smaller epsilon band, even smaller delta. So what happens with the I missed. Got to be like that because what we want is all of the red points to be inside the epsilon band as long as they are also within the delta band. So basically what's happening is you're doing this and zeroing in on that hole, and you're getting closer and closer to that hole. But how big is that hole? The size of the hole is 0. All right, so what this epsilon and delta allows us to do is get closer and closer to that hole, and saying that no matter how close I get to that hole, so for that last epsilon band, I'm saying absolute value of x less than 0.000316 will ensure that absolute value of f of x minus L is less than 0.001. And in general, if the absolute value of x is less than a certain delta, which is whatever the square root of epsilon cubed is, then it will be necessarily true that f of x minus L, the absolute value of that, is less than whatever that epsilon was, where epsilon is any positive number, no matter how small. Oh, look, we got another children's book reference there. Any positive epsilon, no matter how small. That's from what? From what? Horton Hears a Who. People are people no matter how small. Okay, so I think I'm going to talk more about this in our next video.